Okay, so we're going to be looking at the critical points of a function. So the function we're going to be looking at is a function in x and y of 2x cubed minus 6x times y plus y squared plus 7. So to find our critical points, we need to know our first derivatives, partial derivatives in x, our partial derivatives in y, and our second partial derivative is in x, y, and xy. So we'll find all of these. So we'll start first with taking the partial with respect to x. So 6x squared minus 6y for our partial with respect to x. Our partial with respect to y is going to be minus 6x plus 2y. And we'll continue on. We'll find our second partial with respect to x. That's going to be 12x. Our second partial with respect to y, that's going to be 2. And we'll find our partial with respect to xy, or yx, right? Order doesn't matter. So we take this partial with respect to y, we get negative 6. And just to verify, if we take this partial with respect to x, we get negative 6 also. And so we want to find the critical point, so we need to find the place where the the partial with respect to x, the partial with respect to y are both equal to 0. So I'm going to set both of these equal to 0 to get a system of equations. And we can divide the 6's out, so x squared minus y equals 0 at the same time that 2y equals 6x or y equals 3x. So I'll come back in here and substitute. So x squared minus 3x equals 0. I'll factor out an x. And so x equals 0. And that's paired with the y component of 0. So one of our critical points is at 0, 0. And then x equals 3 is the other one, and that pairs with y equals 9. So 3, 9 is our other critical point. Now that we have the critical points, we need to look at how the derivatives, the second derivatives, and the Hessian interact. And so we'll write our Hessian as a determinant of the second derivative spaces. And so what we want here, I think my notes are falling down. Sorry, as I have my answers here. Sorry about that. And so we calculate the determinant by multiplying here and subtracting here. And so this determinant for the Hessian is going to be 12x minus 2 plus, multiplying back up this way, f of xy is negative 6 plus 12. Okay, so is it 12x minus 2? 12x minus 2. Oh, wait, not minus 2. It's going to be 12x times 2, multiplying, so 24x. And then we have negative 6 times negative 6, that's 36, so minus 36. That's our Hessian. And the boundary of the Hessian ends up being our question here. So we'll look at the point 0, 0. And f double x is 0. F double y is negative 6. Or 2. And fxy is negative 6. And our Hessian is going to be negative 36. And then for the point 3, 9, f double x is 36, f double y is still 2, fxy is still negative 6, and our Hessian is going to be 3 times 24 minus 36. So let's see, that's 70. Let's see, 3 times 4, 72, minus 36, which is 36. Kind of a little bit of symmetry going on here. And so if we look at what happens, we have that f of double x is 0. So, and the Hessian is less than 0. So that doesn't give us any information about this point here. But then in here, we have f double x is greater than 0, and the Hessian is positive. So this is a local minimum at 3, 9. Nowhere is the Hessian less, here the Hessian is less than 0. And so this is a saddle point. And if we were to run and graph this, we could see these saddle points happening. And maybe on the next video, we'll look at that. So we have a saddle point and a local minimum.